Today we will discuss the remaining part of theorem 9.8, that the mapping which takes the linear operator A to A inverse is continuous on omega, where omega is the set of all invertible linear operators on Rn. We have already proved part A and half of part B in the previous video. So we have already noted that putting norm of A inverse is equal to 1 by alpha, norm of B minus A equal to beta. Then for every x in Rn, we have alpha minus beta into mod x less than or equal to modulus of bx. And I have already told you in the previous video that this is a crucial result. So to prove that the mapping which takes A to A inverse is continuous on omega, we have to prove that norm of B inverse minus A inverse tends to 0 as norm of B minus A tends to 0, or as beta tends to 0. So we have to prove that as beta tends to 0, norm of B inverse minus A inverse tends to 0, then the mapping will be a continuous mapping on omega. So what we do is, in equation number 1, we replace x with B inverse y for y belongs to Rn. So replacing x with B inverse y in equation number 1, we will get alpha minus beta into B inverse y modulus is less than or equal to modulus of B inverse y for every y belongs to Rn. So this implies that alpha minus beta into modulus of B inverse y is less than or equal to modulus of y for all y belongs to Rn. Okay, or modulus of B inverse y is less than or equal to mod y divided by alpha minus beta. Okay, now so we will calculate what norm of B inverse minus A inverse is. Now we have B inverse minus A inverse. B inverse minus A inverse is equal to say I can write this as B inverse A inverse minus B inverse B A inverse. So this is equal to B inverse A minus B into A inverse. So B inverse minus A inverse is equal to B inverse into A minus B minus A inverse. Okay. Therefore, norm of B inverse minus A inverse is equal to norm of B inverse into A minus B into A inverse. So this is less than or equal to norm of B inverse into norm of A minus B into norm of A inverse. So this is norm of B inverse into norm of A minus B is beta and norm of A inverse is alpha. So norm of B inverse into beta divided by alpha, not alpha, 1 by alpha. Okay, now we have to find out what norm of B inverse is. Now we already have, say if I call this equation star, so from star we can write we have modulus of B inverse y less than or equal to mod y divided by alpha minus beta. This is true for all y belongs to Rn. So this implies norm of B inverse is less than or equal to 1 by alpha minus beta. Okay. So I can write norm of B inverse minus A inverse is less than or equal to beta divided by alpha into alpha minus beta, and this tends to 0 as beta tends to 0, because this alpha and alpha minus beta can never be equal to 0. This implies the mapping which takes A to A inverse is continuous on omega, and that is a proof.